So last time we started talking about chapter 2 really, and measurements and how to take proper measurements. Remember that when we do take a measurement, it's really important to look at the scale on the piece of equipment that you're using and figure out how far you really can take the reading. So we did a couple examples. And again, if we were to look at this particular scale here, we do have sort of the big markings or larger markings, which in this case does represent 1 centimeter. We do want to count up also when we look at a piece of equipment, the smaller markings, and again, try to figure out what they represent. Once again, when we do start counting, we do start at past the last biggest marking. So that would be 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 markings. So once again, in this case, we have 10 markings. The total sort of length measurement here is 1 centimeter. So in this case, each of the smallest do represent 0.1 of a centimeter in this particular case, with something like this being obviously 1.1, 1.2, and so forth. As we talked about last time, you can kind of figure out sort of the precision of an equipment by taking the smallest marking and dividing by 2, which in this case would give you 0.05 centimeters. That's sometimes referred to as sort of plus or minus 0.05. Really what that's going to tell you is how far you can take the reading. And in this particular case, we can take the reading to 2 decimal places based on it. In general, as we talked about, you pretty much can go 1 more place to the right of the smallest marking is typically what you could do. Not in all cases. I think we did an example where you could not do that. But in most cases, that's sort of the general rule, 1 more place to the right of that smallest marking. We, I believe, also talked about temperature conversions, I think, if I'm not mistaken. So we talked about temperature. And again, temperature conversions is the one we use the most is the temperature in Kelvin, is the temperature in Celsius plus 273. Once again, the official number there is 0.15, but most people don't use the 0.15. We also saw that temperature in Fahrenheit is equal to 1.8 temperature in Celsius plus a 32, and temperature in Celsius, temperature in Fahrenheit minus 32 divided by 1.8. So remember that when we're doing temperature conversions, we really don't follow strict significant figure rules, that if all we're doing is really just converting the temperature from one temperature scale to the next, what we're looking to do is just make our converted number look like the original number. So if it was a whole number, you would convert it to a whole number. If the original temperature was like the first decimal place, you would take it to the first decimal place. We also talked about that, why it's important when you do take a measurement, obviously, to record to the proper digits. And typically we always record all of the certain numbers plus that first uncertain number. So this would be 1.3, 1.4, 1.5. So we go something like 1.55 centimeters in this case. And we record all those certain numbers. And that first uncertain number. And remember that when we do that, that is what is basically referred to as significant figures. So this value here would have 3 significant figures. So we also talked, I think, at the very end there that you don't really want to lop off sort of a number in a measurement, especially on a scale like this. Again, if you felt it hit exactly on sort of a small dash or whatever it may be, you do want to still maintain the proper number of digits you should take the reading to. Otherwise, you are making that reading pretty much crappier every time you kind of lop off a number. There's a lot more uncertainty with it. Again, if I recorded 1.5 versus 1.55, 1.5 would indicate that the 5 would be the uncertain number, and it'd be like 1.6, 1.7, as opposed to what it should be here, maybe like 1.56, maybe 1.54. So again, that degree of uncertainty increases if you decide, well, it's not that really important to maintain the proper number of significant figures. Any questions on that there? Okay, so where we left off is to officially talk about significant figures. So let us do that here. As I apparently wrote on the wrong page there. So let me just do this there. Erase all that. There we go. All right, so rules for counting significant figures are as follows. So let's take a look at each of these. First off, when we're counting significant figures, any non-zero number is significant. And when we are counting significant figures, we always start left to right. So in this particular case here, we always start on the left. And we really do not start counting significant figures until we hit the very first significant figure that we have. So in this case, that 1 obviously is a non-zero, which would make it significant. The 2, the 5, and the 9 are also non-zeros, so they would be significant as well. So that has 4 significant figures. Then there's 3 types of zeros that we come across. One is what is referred to as a leading zero. And leading zeros are not significant, sort of like placeholders, if you will. Once again, we start left to right. And we really wouldn't count any of these zeros because we haven't hit the very first non-zero, which would be in this case the 4. And that again is where we should start counting. The 4 and the 9 would then be significant. And this guy would have 2 significant figures, which obviously would be those 2 last ones there, the 4 and the 9. The next type of zero is one that's basically trapped between 2 non-zero numbers. And those are always significant. So our example here of 5.004, once again, starting left to right, we would start at that 5, which is a non-zero and significant. The 2 zeros that are in the middle there would be significant because they are trapped between 2 non-zero numbers. And then the 4 at the end there would also be significant. So again, all those numbers in this particular sort of measurement, if you will, are all significant. So it would have 4 significant figures. Any questions on that so far? Now, the last type of zero is really the one that gives people the hardest time in a lot of cases. And that is what is sometimes referred to as the trailing zero. The trailing zero may or may not be significant. What really determines whether or not those zeros that come at the end are going to be significant is there a decimal point in the number? So is there a decimal point in that number? And if there is a decimal point in that particular number, then all of the zeros so all the zeros at the end will become significant if there is a decimal point. The decimal point does not need to be like hanging out by the zeros. It just needs to be anywhere in that number, and that will turn those zeros at the end significant. So if we look at what we got going down here, we got 600 written like this. This would have 1 significant figure, and it would be this guy right there. And these zeros here would not be significant as there's no decimal point in that number. And we have 600 written like this. Now, because of that decimal point, these zeros here at the end will become significant, and we will end up with 3 significant figures in this particular case. Any questions on that there? Now, 0.001003030. This would have how many significant figures? This was like a measurement. I'm not sure how you get that measurement. Oh, I'm not sure because I was just writing numbers. So let's see here. They're not, because we really haven't hit the first non-zero number. So we would start counting right there at the 1. The 2 zeros in the middle would be significant. The 3 would be significant. These 2 zeros are again trapped between 2 non-zeros, so they would be significant. And then we got the 4 is significant. So are these zeros at the end significant? The zeros at the end are significant because way over here, there is a decimal point. So again, they do not have to be near the number to make it significant, but because there is a decimal point in that number, they would be. And I have no idea how many that was. Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9. Looks like in that particular case. Any questions on that? I believe we also talked about scientific notation last time, right? If I'm not mistaken. And scientific notation, remember that any number that is written in scientific notation, all the numbers before the time part are always. Any questions on that? Also remember, sure, the estimated digit or the uncertain digit, right, is the last significant figure in a sort of number, right? So in this particular case here, the uncertain or estimated digit would be what number? It would actually be the 6, as that is the only significant figure that is there, which means we're basically saying, I think it's 600, but it might be 700, might be 500. So that is where the uncertainty lies in that particular one. For the one underneath it, it is the 0 there, right at the end, would be the uncertain or estimated digit. So it is important to remember that not all the time is the sort of estimated digit, the uncertain digit, always the last one that's written, but it should always be the last significant figure that you have in a particular number. I will say 9 times out of 10 is probably the last one written, but not 100% of the time will be sort of the last one written. Any questions on that there? Now, we do have certain numbers which are considered exact numbers. So there's really 2 types of numbers we come across. One are really measurements and measured numbers, which obviously we do some type of measurement to get those numbers. And there's other numbers considered exact numbers. And there's really kind of 2 ways that we come across exact numbers. So for example, if I have these pens on my desk here, I'm not going to do some type of experiment to figure out how many pens I have. I'm just going to simply count them. So that is one way that exact numbers are reached, and they are determined by counting. So anything that is sort of just kind of counted, not really measured, is considered an exact number. The other, and really probably the most common way that we do come across exact numbers, are in equalities or definitions. For example, 12 inches is 1 foot. 1 inch is exactly 2.54 centimeters. I think she wants you to know maybe 1 pound is exactly 453.6 grams. These are what are considered exact numbers as well. They're definitions. If you remember, there's really kind of 2 types of units that we talked about. And it does come into play in terms of what type of units you're dealing with and exact numbers. But let's first talk about the deal with exact numbers. The deal with exact numbers are, frankly, they could have as many significant figures as you want because they're kind of exact numbers. So they could have an unlimited number of significant figures. Really where this comes into play is what we're going to talk about in just a second, which is when you are doing calculations and you want to give your answer to the right number of significant figures, if it is considered an exact number, you pretty much don't have to worry about it. So you kind of ignore it, even though it's in the calculation. You don't have to worry about how many significant figures an exact number has when trying to determine, for example, how many significant figures your answer should have if you're doing a calculation. You remember there's pretty much 2 types of units. There are English units, and then there are metric units. And for the most part, if you're using a English to English conversion, is considered an exact number. If you're using a metric to metric conversion, it is considered an exact number. Really, the one place where you really should look at a definition if you're using it as a conversion factor in a problem is if you cross over. If you do an English to metric or metric to English sort of conversion factor, I guess however you want to look at it, you should look at significant figures in that conversion factor. And there usually will be a number like, you know, one of something is equal to an actual number of some other unit. And it is the one that has the number as to the significant figures you should look at, not the one. So they're usually like one of this is equal to so many of this. You would want to look at obviously the one with the actual number, not just the one that has the one part of it. We'll look at it in just a second as well. The few exceptions are these couple guys up here. 1 inch is 2.54 centimeters. That's an exact sort of conversion. So even though that's sort of English to metric, you don't have to worry about it. And some people will go with this one as well. 1 pound is 453.6 grams. Not really, 1 pound is 454 grams, but 153.6 is another one. By the way, you should know those two conversions. They do come up a lot. I will say this, that a general thumb, which is, you know, if you're doing nothing but sort of a conversion problem where you start with a sort of a value and then you're going to kind of use some conversion factors to change it maybe to some other unit, stuff like that. I will say probably 9 times out of 10, that original number has probably the right number of significant figures you should end up with. I won't say 100% of the time, but pretty close to it. Even in a situation where you might use some English to metric sort of conversions, a lot of times the actual first number actually has less sig figs than those. So a lot of times you'll be okay in most cases, but again, not 100% of the time. The other place where you would maybe want to use and look at sort of the significant figures in a calculation is if you come across a conversion factor where it's sort of specific for the problem, not like a, you know, there's always 12 inches in a foot, you know, maybe like you're driving so many miles per hour or something like that. So something that's not like a true conversion, but it happens to be related in the problem. So we're going to talk here in just a second about doing calculations of significant figures. But again, if you come across anything that's counted, anything that falls under that definition, you don't have to worry about it in terms of your answer. All right, so take a second here and figure out how many significant figures we got going on in each of those values. Okay, let's take a look, see how you're doing. So once again here, starting left to right, remember we're not going to start counting until we hit that first non-zero, which would be right there at the 3. The 0 is trapped, so that's significant. The 4 is obviously a non-zero. So this guy should have 3 significant figures in this particular case. In this second one, we do have something written in scientific notation. Remember, it is all the numbers here before the times 10 part, which will make it significant. And in that case, that would be 4 significant figures. I will say that sometimes people make a mistake when they have something in scientific notation. They're trying to figure out how many significant figures it is. They will take this number and convert it into like a decimal type number. And they'll go, okay, 2 places to the right. So that's like 127. So it has 3. So remember that if it is written in scientific notation, it's there for a reason. And those numbers are significant. So you don't want to kind of convert it into decimal, then figure it out. Just look at the scientific notation value. Any questions on that there? Here, starting on the left as a 1, so they're all non-zero. So that should be 3 significant figures in this case. Starting on this one here, the 1 is significant. This 0 isn't significant. It is not significant. There's no decimal point in here, so this would just be 1 significant figure. And lastly here, we would not start counting until the 9. The 0 is trapped. The 2 is good. This 0, once again, is going to be significant because of that decimal point that we see there. So it looks like a 4 there, I think, in that case. Any questions on how to count significant figures? All right, so we talked a little bit of the difference between measured and exact. Obviously, if you weigh a patient, that's going to be a measured value. Once again, if you have a basket that has apples in it, that would be more an counted type number, which would be an exact number. The metric system, 1 kilogram is equal to 1,000 grams. So that is a metric to metric conversion. So that is going to be an exact number, really a definition. And obviously the distance is 1,720 kilometers to Colorado or to Texas, one of those. That would be a measured value. Let's talk a little bit about rounding, and it's really important rounding. We do follow regular rounding rules, which means if it's sort of 4 or less than 5, really, we sort of just drop off the numbers to our correct number of significant figures. If wherever we need to end up in terms of significant figures, the next number is 5 or above, we do round up. We also do not want to do any type of crazy rounding, right? So let's say 13,333, and I want 2 significant figures here. What should the answer be? Should it be 2 significant figures would be here? Should 13,000. All right, how about both of those? How many significant figures does the 13 have? Has 2. How about 13,000 the way I wrote it? How many is that? It does have 2 significant figures. So they both do have 2 significant figures, but there's a very big difference, right, between those 2 numbers, right? So for example, if I owed you $13,333 and I said, I'll pay you 2 significant figures, here's $13. I'm pretty sure you're not going to be super happy with me, right? Maybe I don't get out the door at that point. So there's a very big difference in the meaning, obviously, of 13,333 and 13. So although it just does have the right number of significant figures, you never want to change the meaning of the actual number. So if I throw 13,000, like I said, maybe nice, you give me the $333 teacher discount, but for the most part, 13,333 and 13,000 has really the same meaning. And it's very common. People try to get sig figs that they end up, again, laughing kind of changing the meaning of it. So you never want to do that when you are rounding. Any questions on that there? All right, so let's take a look at these. We want to round each of these to 2 significant figures. So 35.723, second significant figure would take us to here. And what should the answer be in this case? Should be 36 meters, as we would look at the 7 and see it's above 5. So we would round up in this case. Coming here, the second sig fig is right about there, which means we would look at the number next to it and we see it's less than 5. So we're just going to drop the rest of the numbers. So that would get us something like 3,800 grams. Do I want to put the decimal at the end of that? I do not, because that would then give me 4 significant figures, right? So here we don't want to put the decimal just because it looks more scientific-y, right? So we don't screw up the sig figs. Looking at C here, we wouldn't count obviously until we hit the 2. And then the 6 would be our second significant figure. So once again, we would look to the number to the right of that 6. We see it's less than 5. So we should end up with 0.0026 liters, right? And lastly, looking at the 2 here, which would be our second significant figure, we go to the right there, we see an 8, which means we should round up, and that would get us 1.3 kilograms. Also a reminder, as we talked about last time, right? Always want to make sure you include the units, right? And everything that you write, not just numbers. Any questions on that there? All right, so more importantly, let's talk about calculations and how we handle significant figures and calculations. There's really kind of 2 groups of calculations that we very commonly do. One is multiply and divide. So when we are multiplying and dividing, the answer should have the same number of significant figures as the number in the calculation with the least number of significant figures. So when we multiply and divide, we're looking at significant figures and we're looking at the least number of significant figures as to what your answer should have. So for example, if I took 4.25 and times it by 1.2, we're multiplying. So we look at sig figs. This guy has 3 sig figs. This guy has 2 sig figs, which means my answer should end up with 2 significant figures when I do the actual multiplication part of it. Now, the other sort of type of measurements are sort of process that we do is addition and subtraction. And addition and subtraction, we're actually looking at something different than significant figures. We're actually looking at decimal places. So when you add and subtract, you want to look at decimal places. And it again is the one with the least number of decimal places. So the good news is it's always the smallest, least, however you want to word it. One is significant figures, but adding and subtracting is the least number of decimal places. So if we had something like 2.55 plus 1.3, and give it a try without the calculator. That's like a 5. That's an 8. Maybe that's a 3. At this point, when we look at our final answer, we're adding. So this guy has 2 decimal places. This guy has 1 decimal place. That means really we should go to 1 decimal place. Once again, we would look to the right there and we see a 5, which tells us we should actually round up in this case. And our correct answer should be 3.9. Any questions on that? 3.9 has 1 decimal place, but how many significant figures does it have? It has 2, and that's really important in case you go and take that number and continue on with more calculations where maybe you're multiplying and dividing. So, you know, you can absolutely have multiple things happening at once in a calculation. So if you have 32.55 times 423 divided by 16458. In this particular case, math-wise, we would do what's on top there, and we're multiplying. So we have 4 significant figures on the left. We have 3 significant figures on the right. So technically 3 significant figures is how much the top part of that calculation should have. The last math that you would do is you would take that top number and divide it by the bottom number, which means you're still looking at significant figures. So that would be 3 significant figures divided by the bottom, which is 5 significant figures. That means your answer should end up with 3 significant figures. So you do want to sort of keep track of everything along the way in your calculation and give your answer obviously to the right number of significant figures. Any questions on that there? Couple of things I would say outside of a straight significant figure sort of question. In most cases, when you're doing a calculation and maybe you're going to take a number and then do another calculation with it, and maybe going to do another calculation with it, you really don't want to round until kind of the very end. So it's always good to keep several digits past the proper number of significant figures and then really clean it up at the end. So sometimes people use a guard digit where they put a little number over where it should end and then they keep some digits. You don't have to do that for me, but if you want, you can. But in your calculator or on your paper, you should take a few more digits than the actual correct sig figs if you're going to take that number and continue on with the calculation. Problem is, if you take a number and round really strictly and then take that number, do a calculation, round again, do a number and round again, you're really just going to be moving yourself farther and farther away from probably the correct answer. So the general rule is try not to round to the end, but you do need to keep track of all your calculations and really where you should end up with in terms of significant figures at the very end. And then you should obviously clean it up at the very end of the calculation. Any questions on that? Couple of reminders as well. Your calculator does not give you your answers in the right number of sig figs, right? And sometimes may not give it to you in scientific notation either. So keep that in mind as you give answers. All right. All right, take a second and round these guys off to the proper number of digits here. See what you come up with. Take a look. So we got our answers given to us. We just want to round them to the proper digits. So in the first one here, we're multiplying. So we want to look at sig figs. That's going to be 3 sig figs. That's going to be 2 sig figs, which means we really should end up with 2 significant figures, which puts us there. We do look at the number next to it, which is a 7, which means we should end up with 9.4 in this particular case. Looking at the next one, we're dividing. So once again, we're going to look at significant figures. So that guy there has got 4 significant figures. This guy's got 3, which means our answer should end up with 3 significant figures, which would actually put us right about there. And we would look at the number to the right, and we would just drop it. So 0.0758, it looks like in that particular case. Any question on those first 2? Here we are adding. So remember, when we add and subtract, we're actually looking at decimal places, not significant figures. So here, that is 2 decimal places. That's 1 decimal place. That is 3 decimal places, which means our answer should end up at 1 decimal place, which would be right about there. And that would be 29.1. Again, it has 1 decimal place, that number, but it does have 3 significant figures in that case. And lastly, here we're subtracting. So once again, we're going to be looking at decimal places. So that is 4, that is 1, which means we actually would go there. Looking at the number next to it, which would be an 8, we would round up to 0.6, it looks like, in that particular case. Any question on any of those? So adding, subtracting, you're going to be looking at decimal places the least. Multiplying, dividing, you're going to be looking at significant figures the least. And really why it's the least is, frankly, it's your worst measurement. So your measurements and your calculations are only as good as your best or your worst measurement. And in each of those cases, that would be your worst measurement. Obviously, in a calculation situation like this, if we probably more so with multiplying and dividing, if we came across one of those definitions or stuff like that, that's an exact number, we just ignore it. We don't even worry about it in terms of sig figs. Again, unless it's a metric to English sort of conversion, and not one of those exact conversions. Any questions on calculations of sig figs? All right, so I think we talked a little bit about this last time, but this again is the way we change our metric system. And I think they kind of want you to use these, but you can use these as well. More importantly, as we talked about, you want to make sure that you do it correctly. So once again, if you had 1 centimeter, that would be 10 to the minus 2 meters. So what we see on this side, and really even this side as well, is how much there are again in the base unit to 1 prefix unit. So again, it's a very common thing that people really reverse around all the time. Again, you can divide both sides by 10 to the minus 2, and you'll get the 100 centimeters is in 1 meter. So that's how you could kind of convert it the other way, by dividing it to the other side. Each of these on the right, again, are 1 times those guys in scientific notation, basically. And again, it doesn't matter the actual base unit. So if you had 1 kilogram, that would be 10 to the 3 grams. So again, that is the proper way, or 1,000 grams in a kilogram. That's the proper way to use those conversions. And you do need to kind of know those. So again, kilo, centi, milli, I would say maybe nano will come across a lot, but definitely you should have, at least probably in here, known. Any questions on that? All right, so we talked a bit about some length equalities earlier, so we won't go spend too much time on these, but again, these are some common equalities that we use a lot. I would say, once again, this one we do use a lot, and that one does pop up occasionally. Definitely this one we use a lot. 1 liter is 1,000 milliliters. Pretty much all the time that comes up when we're doing things with solutions. And a relationship that we talked about as well in terms of volume. Remember that you could get a volume basically by reading the volume, but if it's some type of solid like we have here, and we did the other day and we'll do today as well, you can measure the length times the width times the height, each of them in centimeters. Each of these individual measurements are length measurements, but when we multiply them together, it does become a volume, right? Which is what each of these are. And again, 1 cubic centimeter is equal to 1 milliliter. Cubic centimeters used a lot for solids and liquids a little bit, but milliliters are also used for obviously volume and liquids. Remember as well, when we talked about measurements, we always want to read from the bottom of the meniscus, right? That curvature of the liquid. And again, the scaling could be different. So for example, in this particular one, there is 10 milliliter difference in terms of the big markings. There's 5 markings, right? Which means in this case, each one is actually 2, right? Milliliters. So again, not always first place to the right. You do want to make sure you look at those markings and figure out how far you can read it in this particular case. Mass, kilograms, and milligrams. I would say these top 2 come across once again a lot in chemistry. And obviously we measure it using a balance. All right. I think we'll skip these real quick. Let's talk a little bit though about writing conversion factors. So we do use conversion factors in chemistry a lot, and we do solve problems through a process known as dimensional analysis, which we'll talk about here in just a second. But really a conversion factor is found from any type of quality. And a quality, again, is really 2 values that are on different scales, but represent really the same amount of something. So if we had 100 pennies, that would equal $1, right? They both represent the same amount of money, just different units. If we had 12 inches is 1 foot. And really from any one of these things, which are equalities, we could write 2 conversion factors, and conversion factors really are nothing more than fractions, where we put one quantity on top and the other quantity on the bottom. And we use it in problem solving, dimensional analysis way, which is how they want you to show your work in chemistry for sure. And that is where we do it, where the units cancel. So for example, if we had 4.5 feet and we want to know how many inches that would be, we would actually take the conversion factor on the left and set it up so we could see the units cancel. And basically when we're doing this type of process, it's opposites cancel. So although this is not written as a fraction, the feet are up on top. So to get rid of them, the feet need to be on the bottom. It's the same thing. If you took 2 divided by 2, it equals 1. If you took feet up on top and divided it by feet, it would equal 1. So they essentially cancel each other out, the actual units. And what we're doing here is multiplying everything on the top and then coming back and dividing by whatever may be there on the bottom. In this case, they're all 1s, not much dividing. So in this particular case, we would multiply 4.5 times 12 gives us 54 inches. Once again, the feet will cancel, leaves you just inches up on top. In terms of significant figures, this guy here would be considered an exact number, so we would not look at it, which means really the only number that we have is the 4.5, which has 2 significant figures. And we pretty much did multiplying and dividing here, which is pretty much what you do in these type of dimensional analysis problems. And that means we should end up with 2 significant figures in this case. So once again, exact number, don't have to worry about sig fig. Most cases, you'll default back to this guy, 2 significant figures here. Answer should have 2 significant figures with the correct number of units. Any questions on that there? Pretty much what I just said. Here are some common equalities. And again, as we talked about, US is kind of like the English measurements and our metric there. And then we have metric to US. So obviously this comes up a good amount. That one does as well. That obviously does. All of our sort of length measurements we talked about earlier. Our volume ones and our mass ones do come up a lot. These are metric to English. And again, that's considered an exact sort of definition. Once again, if you are using some type of conversion factor that came from sort of that category, if you will, you again should look at the significant figures in that. And as you can see here, for example, 1 meter is 39.4 inches, or 39.4 inches is 1 meter. If I use this in a calculation and I want to look at sig figs, this is what I was talking about earlier. We would actually look at the sig figs in the actual number, not the one that's a 1. So obviously there's always going to be a 1. So you want to look at that and you go, okay, this guy's got 3 significant figures. And is that more or less than obviously somebody else? So that's what I was mentioning about earlier. If you're kind of crossing over, you don't look at the 1 because it's always going to be kind of 1. But you do look at the one that has the number and figure out how many significant figures. Anything that's in these 2 categories pretty much, or any other ones that fall into those categories, you don't have to worry about the sig figs in the actual conversion factor. Any questions on that? All right, so if we were going to write a couple conversion factors here, 5,280 feet is 1 mile. So we would have 5,280 feet over 1 mile, or you could write 1 mile is 5,280 feet. Once again, you would not use both of them. You would just use whichever one, obviously, you needed to use, where the units would be opposite. So if I had 42 feet and wanted miles, I would use the one on the right here. That way the feet cancel. We would take basically 42 and divide it by 5280. Now, we sometimes have things in words or something like that, but if we're driving 65 miles per hour, something per something is really a fraction. So basically what that means is you're going 65 miles in 1 hour, or in 1 hour you could drive 65 miles. So once again, you would choose whichever one would be appropriate here. In this particular case, since this is not a really true conversion, it's really specific for probably a problem you're doing. You would probably want to look at the sig figs here in the 65 and compare them to the other numbers in this particular case. My 91 octane costs $3.05 a gallon. Yes, where can I find that? All right, so 1 gallon is $3.05, or $3.05 is 1 gallon. It used to be expensive when I wrote this slide years ago. Now everybody would run for that, I think. And a very common thing that we do come across a lot in chemistry is sometimes we're given numbers in percentages, and we want to turn them into sort of a usable conversion factor. And really the best way to do that is to assume that you have 100 of something, right? So it keeps really the percentage the same, or the numbers the same. So if you had 12% body fat by mass, you could say that would be 12 kilograms of body fat per 100 kilograms of body mass. And again, you could have your 2 conversion factors that you could use. You could also use more of an English sort of conversion, 12 pounds and 100 pounds. And you could get your 2 conversion factors from there. So very common percentages can be turned into usable conversion factors by assuming 100. And it again allows you to do a dimensional analysis sort of calculation. Any questions on that there? All right, so dimensional analysis, as I mentioned, is the method that they want you to use in chemistry. As you continue through your chemistry goal, you usually will have some type of equality. And you always want to set it up where we can see the units cancel. So again, opposites cancel the units. So if it's on top, put it on the bottom. If it's on the bottom, put it on top. And this again is the way they want you to show your calculations. set up just like this where you can cancel those out. By the way, if you have multiple steps along the way, let's just say maybe we're going to go to unit C. You just continue on in that process. Unit B is up on top. So we would put unit B on the bottom to get rid of it, and that would leave us unit C on the top. Again, we would be multiplying across the top, coming back and dividing across the bottom. So that's mathematically what we're doing. If you have multiple sort of conversions to do, you could just do them all in a row. Any questions on that there? Okay. So here are the steps to follow when you're doing dimensional analysis problem. You want to write what's given to you. You want to think about what you want to find. You want to find all the appropriate equalities and conversion factors. You want to set up the problem using dimensional analysis that the units cancel, and then you obviously should solve it as well. Do you need to do all these steps? You don't, but you do need to make sure you show the work. So let's take a look at one here. Obviously, in this case, this would be a very simple example. How many pennies are in $3? That would be our equality, which would be $1 is 100 pennies. Those would obviously be the two conversion factors that we could get from it. We would start with, our given, which was $3. Again, not written as a fraction, but that means those units are up on top. So to get rid of the dollars, we want to go opposite here, which would give us 100 pennies in $1. The units here will cancel. We're going to multiply across there, giving us 300 pennies as our answer here. In this case, this would be an exact number, which means we would default back to this guy here, which would have one significant figure. So we'll end up with one significant figure in this particular case as well. Any questions on that straightforward one? Okay, so why don't you try one here, I think. All right, you go to 7 a.m. p.m. and get yourself a 32 fluid ounce drink of Diet Coke. How many gallons of Diet Coke did you drink? Set it up using dimensional analysis and see what answer you come up with. There are some equalities and conversion factors that might be helpful here. Let's take a look. So again, we're going to start with what was given, which is 32 fluid ounces. Once again, not written as a fraction, but basically fluid ounces are up on top. So we want to go opposite to get rid of it. So we would want to use that as our first conversion factor, which would be 32 fluid ounces is 1 quart. If I stopped the calculation right at this point, fluid ounces would cancel out and I would be left with units of quarts, which is close to what I want, but I want gallons. So we'll continue on with our next conversion factor. Once again, quarts are up on top. So to get rid of it, we want to go opposite with that unit. So continuing on here would give us 1 gallon is 4 quarts. Once again, the quarts on top, the quarts on the bottom will cancel each other out. We're going to multiply everything across the top there. So basically 32 times 1 times 1. We're going to come back and divide by 32 and then divide by 4. And you should end up with a 0.25 gallons in this case. You should not end up with 1/4 because that makes me think you're just too lazy to actually divide it. Yes. So don't ever leave an answer in fraction form. Make sure you divide it out and get an actual number with a decimal if necessary. Any questions on that there? Once again here, kind of in the middle, really would be considered exact numbers. So defaulting back to our original number, which was 32, has 2 sig figs. Answer at the end there has 2 sig figs. Any questions on that one? All right, let's try another one here. We'll try this. Antibiotic dose is given as 500 milligrams. If it comes as 250 milligrams in 5 milliliters, how many milliliters would be given? Take a look. So in this particular case, we actually have a conversion factor kind of given to us in the problem, which is really where that comes from. And really, you can use it either way. If you, for example, needed the milliliters up on top, you could do that as well. Oops, 250 milligrams. So in this case, we're looking for a 500 milligram dose. So that would be 500 milligrams. Once again, dimensional analysis, we do want to get rid of the milligrams. So we will use the conversion factor over here on the right, since it's an opposite location. That's going to give us 5 milliliters, 250 milligrams. Milligrams will cancel. We're going to multiply the top there. So 500 times 5 divided by 250 will yield us a 10 milliliters in this particular case. Now, in terms of significant figures, this is really not a true exact conversion. It's just really what's given in the problem. So we should look at sig figs there. So we do have 5, which has 2 sig figs. This also has 2 sig figs. This has 3, as I lost the decimal point up there. So our answer probably should end up with 2 significant figures, since we're multiplying and dividing in this case. Any questions on that? All right, so during surgery, a patient receives 5 pints of plasma. How many milliliters of plasma were given? Here's a few conversion factors and stuff. Why don't you give that a go? Okay, so let's take a look. So in this case, we've got 5 pints. We want to know how many milliliters. Once again, obviously these won't be provided for you, right? You have to go find them and figure them out. But these are the equalities and stuff that we could get there by, and our conversion factors. So we'll start with our 5 pints. Once again, pints are up on top, so we want to get rid of it. So conversion factor there on the left will do that. 1 quart is 2 pints. We stop right there. Our pints are going to cancel each other out. We're left with quarts. We do want to get to milliliters, so using the conversion factor here on the right, we'll do that. It's opposite. So quarts are on top. We'll put quarts on the bottom. Our 946 milliliters. Quarts will cancel, and we will end up with about 2365 milliliters. Looking at sig figs, again, probably can ignore these guys for the most part, since this is the smallest number of sig figs we have, which is about 2. That means we should go here. We should round up like a 2400 milliliters would work. Or if you want to do scientific notation, 2.4 times 10 to the 3 milliliters would also work. Any questions on that there? So let's take a look at one more here, I think. You're stranded 125 miles away from home, and you decide to walk it. You walk 55 feet per minute. How many days would it take you to get home? Okay, let's take a look, since we're getting kind of to the end here. So we're definitely going 125 miles, which is a length. We do have a rate, which is really sort of our length, our distance per time, which is our feet per minute in this particular case. We do have a little bit of issue before we could really use them together. The rate there is going to allow us to go from really distance to time, but our sort of distance or length measurements are obviously in different units. So we do need to do some type of conversion first to be able to use it. To either convert the feet to miles or the miles to feet. I'm going to choose to convert the miles to feet here. So that's where I'm going to start. I'm going to go with the 125 miles. I'm going to use this as a conversion factor here. So opposites My miles are going to go on the bottom, and that'll be 1 mile and 5,280 feet in this case. Miles will cancel. Going to give us something like, I think, 660,000 feet. Seems like a long way to go. So that is what we're going to use here, 660,000 feet. And once again, now we have it in feet. We could use really our rate as a conversion factor. We use it just the way it is. If we needed to, we could obviously flip it the other way. And that is what we need to do. We need to put the feet on the bottom. So that would give us 55 feet per minute. And it's that part where the feet are going to basically cancel. We're now left in minutes, which is a unit of time, which is ultimately what we're looking for, some type of unit of time. Now it's just a conversion between minutes to days. So you could go, there are 60 minutes in 1 hour. The minutes again will cancel as they are opposite. And remember that there are only 24 hours in a day, not 60. Sometimes people go 60 seconds, 60 minutes, 60 hours. So it's only 24 hours in a day. Once again, we want to go opposites here. Hours are up on top. So 24 hours on the bottom, 1 day. Hours will cancel. Once again, we're going to multiply all the way across the top, which is basically all ones. We're going to divide by the bottom, which is an error. Try to get 66. Nope. 660. Divided by 55, divided by 60, and divided by 24. Going to yield us like 8.33 days in this particular case. Seems like a nice walk, I suppose. 3 sig figs, because frankly, that had 3 sig figs, that had 3 sig figs. So our answer should probably end up with sig figs, as pretty much all the rest of it there is sort of exact numbers in this particular case. Any questions on this calculation? This is how you need to show your work, dimensional analysis with the units. Do you need to show all this? You do not. You need to show all this with the right answer, right sig figs and all that. But it helps you to show the conversion factors and all that, do it. But you don't need to. This is what you need to show, the setup like this we see here. One thing about calculators, again, if you were going to punch this into your calculator, I'd multiply as many numbers as you like out of the top, hit equals, divide by the first number, hit equals, divide by the second number, hit equals, and then divide by the last number and hit equals. Try not to put it all in at once, otherwise you might get the wrong answer. Any questions on anything we talked about here? All right, we will lay it up there for lecture today.